So welcome to this lecture of mixed signal IC design. So in the previous classes we were doing unit 2 where we were focusing on the study of op amps, and if you remember we did a review of single stage amplifiers, especially CS amplifier, and that was basically that was done to understand about the frequency compensation, and with that we extended that to the study of two-stage op-amp, the architecture with the design from specification, and also we looked at the compensation method, Miller compensation method, and also zero nulling resistor to um, cancel or to nullify the effect of the right half plane 0. That is what we have done in unit 2. There are a few more other things we need to discuss in unit 2, but the main portion is done with unit 2. So today we'll go ahead and we'll start with another important building block of data conversion system. That is nothing but a comparator. Alright, so today the time what we spend, we'll be discussing more about comparators. Alright, so what comes to your mind when you hear this word comparator? When have you come across this comparator before? You can use the chat window if you want to. Are you guys there? Can I get some response in the chat? All right, Anish, yeah, designed to square wave converters, where I think you have done that in your analog microelectronic circuits, where you have come across something called a Schmidt trigger. It's a form of a comparator, right? All right. Apart from that, I am sure that in your third semester analog microelectronic circuits course, you have come across comparator as zero crossing detectors, or different versions with respect to op-amp by giving different reference voltages and stuff, right? So here when we discuss about comparators in this course, one thing what we should understand is this is one of the most important mixed signal block. I can say this is one of the most important mixed signal block which is used other than amplifiers, right? So we have discussed about amplifiers, op amps, and the second most widely used electronic circuit block after amplifiers are comparators. All right, so generally what you understand by comparator is, from the name itself, generally we used to I can say that a comparator, it is basically used to detect a signal, basically to detect whether a signal is greater or smaller than a specific reference voltage or a zero voltage, right? So this is used to detect whether the signal what we have is greater or smaller than the reference voltage. In general, we will write this as smaller than 0, greater or smaller than 0, or generally to compare the size of one signal to the another, right? Or to compare the size of one signal to another signal. That is how generally comparators are used. All right. Now, in our course, especially in this mixed signal IC design course, we use comparators, and this comparators is widely used in data converters. I am sure that you would have heard about comparators, even in the other courses. Say, for example, in your communication course also, you would have definitely heard about comparators, where especially when a signal travels through a channel, you use something called as regenerative structures, like regenerative comparators, in order to restore the signal level back. Right, so there are different scenarios. The comparators are used even in memories. There are different scenarios where we use comparators, but in our with respect to confining to our course, these comparators are widely used in data converters, or I can say it is a heart of a data converter. Comparators forms the central block of a data converter. Or so if you look at comparator, what it basically does is it compares the signal, the signal what you have with a reference, and decide whether the output goes to a higher reference value or a lower reference value, right? So in fact, comparators can be considered as Comparators are in fact 1 bit ADC, where the output says whether the input signal level is higher or lesser, higher or smaller by coming to a logic value, whether it is 0 or a 1. Alright, so generally how you represent comparator is, we represent comparator as a block where you will have two input signals. Single-ended comparators, I'm just marking about single-ended comparators, where you will have an input voltage which need to be compared with a reference, and I call this as, say, my reference. Now input and reference is compared, and the decision is made here, and that is available as a form of output, right? So what do you think this comparator operation, whether it is a linear operation or a non-linear operation? What do you think about this comparators, whether it's linear operation or non-linear operation? Can I get some response in the chat? It is non-linear, right? So generally we represent comparator in this form. Either the output will go to high or the output will come to low. It's a non-linear operation. All right. So what we expect here is V out will be either 0 or 1. If your input voltage is less than Vref, what we expect is a 0. If your input voltage is greater than Vref, what we expect is 1. Right. But it is not mandatory that the output voltage, what we say, this V out need to be always, it is not mandatory. So let me write it like that. Yeah. So V out need not be always a 0 volt or a 1 volt, need not be always like that. It can be any two discrete levels. It can be any two discrete levels. All right. So just to add on that, just to explain over that, say we have a set of input voltages, and we want to find what is the I want to see how the comparator will respond to these set of input voltages. Say for example you have and you have reference voltage as well. Say your reference is 0, and the inputs what you have, if the reference is 0, if you have, say for example, a 0.2 volt, so 0.2 volt is your input, then since the reference is 0, the expected output is high, the high value, it can be 1, it should be 1. And if your expected value is, say, minus 0.2, since it is less than 0, your output what you are expecting is 0. Right. Now when we say this, when we write this as 1 and 0, it need not be always 1 volt and 0 volt. It can be any two discrete levels of voltages, that is possible, right? And what we also expect from a comparator is it should compare and give us a decision, give us an output voltage, even if the input is very, very small. Say for example, if an input is 0.0001, or if your input is 0.001, in all these cases, if your reference voltage is 0, what we are expecting is actually 1 as the output. All right. And so that means that comparators are not just to compare between two voltage levels which are large. Comparators should also respond and make a decision even if the input voltage is small. So basically that we call as the smallest resolvable voltage, or we call it as the with respect to ADC we use the term called as LSB. All right. Now the question what I have now is, okay, straightforward, I'll come to this. All right. My question is, can we use an op-amp? Because we have discussed about op-amp in the previous unit. Now the question is, can we use an op-amp as a comparator? Can we use op-amp as a comparator? What do you think? Can I get your response in the chat? Yes, we can use op-amp as comparator. So do you think is there any limitation in the use of op-amp as comparator? Um, all right, let's see. Yeah, op-amps can be used as comparators and plus VCC and minus VE. Yeah, those are voltage supply limits. All right. Yeah, so op-amps can be used as comparators, and if you remember, you have looked at various those levels of comparators, right? In the previous courses, op-amps can be definitely used as comparator. But let's see whether op-amp using op-amp as a comparator in these days, especially when we talk about ADCs and DACs, ADCs which works at high rates, which can sample like say giga samples or like high mega samples. In that kind of ADCs, can we use op-amps as a comparator? Is the question. If I just elaborate the question what I intend to ask is that can we use op-amp as a comparator even in high speed ADCs? All right, let us look at this scenario. Say I have a 1 volt supply. Like I have a block which works on 1 volt supply. What I meant is an ADC. Say the number of bits in an ADC is 10 bits. I have a 10 bit ADC which works with 1 volt supply. Now, can you tell me what is the minimum resolvable voltage of this? Minimum resolvable voltage for this ADC. We call this minimum resolvable voltage as LSB, the least significant bit, or we call it as 1 LSB. We will talk about this in detail in the later half of the first unit, so the third unit, and in fourth unit in detail. Yeah, yes, Anish. So the minimum resolvable voltage is, if we have 1 volt as a supply, 1 volt divided by the number of levels in ADC. If you have a 10 bit ADC, you have 2 to the power of 10 levels. So it is approximately 1 by 1024 is the minimum resolvable voltage. We will discuss more about this as LSB in the subsequent classes. So for now, if I look at this in terms of voltage, this will be approximately, I think this is equal to some 975 or 976 microvolt, right? Or I can think this is very close to some 1 millivolt. Alright, so this is the minimum resolvable voltage if you work with 1 volt power supply with a 10 bit ADC. Now, so say for example, I just want to use op-amp for the comparison operation, and say if I look at the gain requirement of an op-amp, required gain for an op-amp will be how much? Can you tell me what will be the required gain for an op-amp? The total supply voltage we have is 1, and the minimum resolvable voltage we have is 975 microvolts. So this required gain will be naturally, we can write it as VDD, the power supply, divided by approximately 1 LSB, or it is exactly half LSB, but still, yeah, we'll write it as 1 LSB only. So 1 divided by some 975 microvolt. Or this is a value, the required gain will be approximately 1000 or more than 1000. Are you guys with me? Can I get some response in the chat? Can I get some response in the chat? Are you guys with me? Yes. So the required gain for the op-amp is closely 1000 or more, right? Now, in the previous classes, you remember we were discussing about op-amps, especially the frequency response. Say if I look at the frequency response of an op-amp, this is the frequency axis. This is frequency axis, and here say I can mark it as this is the DC gain A0. What is the requirement what we have written? But we know that op-amp is not something which is having an infinite bandwidth, rather it is having a finite bandwidth. And usually the finite bandwidth, or the first pole, what it comes, we call it as even 3 dB frequency also, the first pole, right? That usually defines the bandwidth of the system. And after that we expect something of this curve. We know that in the previous case, in the case of two-stage op-amp, we had 2 poles, and what we did is by compensation, generally we work with circuits which is compensated. If it is compensated, it looks like as a first order system which is having a single pole, and this defines the 3 dB frequency. The first pole the dominant pole will decide the bandwidth, and here you will have the gain bandwidth, unity gain bandwidth, UGB also will be here. Alright, now let's assume that the unity gain bandwidth is around 100 megahertz, which is a reasonable value. Now with the required gain, say if I am looking for a gain of 1000, what will be the 3 dB frequency, or what will be the bandwidth of this system? How can I get bandwidth? We know that gain bandwidth is the DC gain into the bandwidth is f3 dB. So f3 dB can be written as the gain bandwidth divided by the A0 value, so which is closely equal to 100 megahertz divided by somewhere around 1000, so which will give a value close to what will be the 3 dB frequency here? Some answers in the chat. Yeah, close to 100 kilohertz. So the bandwidth or the 3 dB frequency what we are expecting is around 100 kilohertz. Now till now we did not talk anything about the time domain aspect, right? But now when you have a 3 dB bandwidth of 100 kilohertz, that corresponds to, we know that 3 dB bandwidth is equal to 1 by 2 pi RC, which is which can be written as 1 by 2 pi tau, where tau is the time constant of the circuit, right? Now if I look at this tau factor, if I want to get the value of tau factor from this 3 dB frequency, which is 1 by 2 pi f 3 dB, I can write this as 1 by 2 pi into basically 100 kilohertz, which will give you a value very close to, say for example, in this case it is 1.59 microseconds, right? So what we have done is, I'll just come back. Now if your time constant is 1.59 microsecond, and let's say it takes for the circuit to settle, if it takes some 3 to 4 microseconds, say if I am considering 3 to 4 times of this tau, this is approximately equal to if I am multiplying with 4 into say 1.59 microseconds is closely equal to somewhere 6 microseconds, right? That means the maximum rate at which we can compare a signal, say for example if I am using an op-amp to compare two voltages, the maximum rate at which I can compare will be in accordance with this tau, with this time constant, right? Or to be very precise, I can write here that this exactly if you write it is 6.36 microsecond in this case, this corresponds to the 6.36 microseconds corresponds to a sampling rate of 1 by tau, right? A sampling rate of what is 1 by 6.36 micro? This will be very close to somewhere around 157 kilohertz, right? So 6.36 microsecond, there is a time constant which we assume that the voltage will settle with that time, so that corresponds to sampling rate of around 157 kilohertz. So that means the maximum rate at which you can compare two voltages is only 157 kilo samples per second. Alright, so which is less compared to what we have today, because nowadays ADCs work in gigasamples per second rate. Alright, so this is less compared to the requirement or the gigasamples per second ADC is what we have. Are you guys with me? Are you like getting the plot what I am doing here? So I am just discussing whether we can use the op-amps what we have learned so far as comparator. Definitely there are cases where we can use, but the limitation there is a speed limitation, because especially when you have an op-amp which is compensated will have less bandwidth, right? Well, when you compensate an op-amp, what happens is your bandwidth is we are actually compromising, and the trade-off factor there is bandwidth, because we are pushing the dominant pole close to origin, thereby we are reducing the bandwidth. So that is in turn that will affect the speed. So I cannot use all the op amps which is a compensated op amp for the speed like for high speed applications. I cannot use op amps as such. Does it make some sense? Can I get some response in the chat? All right. So I'm just on the concluding statement. What I'm writing is op amps are therefore generally not preferred. Now, one more thing you can look at here, because when we were looking at the operation of a comparator, we saw that it is not a linear operation what we have. The moment we talk about operational amplifiers, and what we try to do there is actually what to say, a linear operation, right? Because in general in amplifiers we talk about a linear amplifier. What we try to always characterize is what we try to do is to make a linear amplifier. But the Cara what we exactly need in the case of a comparator is a non-linear Cara. So for that reason we are not that interested to continue or to design linear amplifiers and use in that purpose. In fact, when the moment you say op amp, we'll be definitely using it in open loop configuration also. All right. Yeah. So for the said reason, we generally will not prefer op amp. So why I am focusing on to this point is the comparators what we are going to discuss in this course, in this specific unit, is not op amp based comparator, but other comparators. But before going to the other type comparator, let us see how I can use an op amp comparator. Generally how people use. So that I'll take as an approach 1. If you have questions, please put it in the chat box. Say for example, if you want to use op amps as comparator, generally the approach is actually to use a cascade of amplifiers. Cascade of amplifiers approach. So what we do is, so what I want to know is, say for example, you will have some voltage on a capacitor. You will have some voltage. Now I need to know whether this voltage is greater than or lesser than a specific voltage. For say the reference voltage is 0. So if you have some voltage here on a capacitor delta V, because when you talk about comparator, you can also think about the previous stages what we discussed. You will have a signal, you will sample it, you have a sample and hold circuit, and you are getting the signal. Then we spoke about amplifying those signal with the help of switch capacitor integrators and other things. Now if you have a signal on a capacitor, now how you can compare and make a decision whether that signal is greater than or lesser than a reference voltage is what we are going to do now. Now if you have a voltage, a small voltage in a capacitor, now in this approach of cascade of amplifiers, what generally do is we use a series of cascade of amplifiers. How many stages we want, we can use, right? It is not like we can generally use so many stages, because we need to integrate all these things into an IC. So if all amplifiers have gain A, so after every stage, so finally the output here, if you take output at one specific, if this is the output point, your output will reach certain level, right? That level will be either close to your supply or close to the ground point. So all these amplifiers are connected together, and say this is connected to VDD, and this is connected to say VSS voltage, right? Or this can be ground as well. Now since I am taking my reference voltage as 0, I'm just marking it as VDD and VSS, right? So at this point here, the output will Vout will reach a certain level. Whether it will be the decision based on the decision made, whether it will go to either to VDD or it will go to VSS, right? Now can you tell me what is the minimum voltage what I can resolve in this setup? What will be the minimum resolvable voltage? Say we have three stage. So, say for example, you can consider that three amplifiers in cascade. What will be the minimum resolvable voltage? The supply rails, the maximum possibilities VDD minus VSS. VSS should be, in this case, VSS is negative. So minimum resolvable voltage will be, this is the possibility, this is the entire supply voltage range divided by, if I am using three stages of amplifiers, three stages gain, say for example A cube, right? So this is the minimum or the smallest resolvable value will be this. Like, are you guys with me? Can I get some response in the chat? Yeah, so I'm just looking for what can be the minimum voltage here. So if I have the supply rails range divided by the total gain will give you the minimum resolvable voltage, or in turn you can write that gain is nothing but the maximum output divided by the minimum input. In that way I have written. Now in this case, if I want to increase the resolution, or if I want to increase, or if I want to make the minimum resolvable voltage still smaller, what I should do? That means if I want to increase the resolution, what is the thing what I can do here? Some response. Yeah, increase gain. So increase gain is generally by adding amplifiers. That is what I can do here, right? Now as I mentioned, if I want to increase gain in such a fashion, you have to add a lot many stages of amplifiers, and it will have definitely have its own what is it, drawbacks of bringing in so many amplifiers. Then regarding its speed, regarding the noise, there are a lot many other things we need to consider, and including this, and for the before mentioned reasons, we will or at least now we are actually looking for comparators which are not out of the regular amplifier stuff. We are actually looking for we are going for some other approach. All right, so with that I am just introducing, I will write here as approach 2, where will not be using directly any op amps, rather we will be seeing how we can get a comparator without op amps, right? For that, let me take the same case. I have some voltage here on a capacitor, say delta V, and I want to know, the requirement here is I want to know whether this voltage delta V is greater than 0 or less than 0, right? So I have delta V. Now the requirement is to find whether this voltage what I have across a capacitor is greater than 0. Instead of writing as Vref, I am just taking it as 0, greater than 0, or delta V less than 0. This is my requirement, right? Now say say for example, if delta V is greater than 0, what am I expecting? The scenario here is I have a voltage, I have a capacitor here, it is carrying some voltage. Capacitor stored some voltage delta V. Now I need to know whether this delta V is greater than a reference value or lesser than a reference value. And now say for example, if I know if delta V is greater than 0, what am I expecting? What am I expecting the output should be? If the delta V is greater than 0, what should be the output? Yeah, it should go to high. That means if delta V is greater than 0, I should make an attempt. An attempt should be made to increase it, right? In a similar way, if delta V is less than 0, attempt should be made to decrease the value, right? That means or this should actually happen. So when I say an attempt should be made to increase it, in the sense what I meant by that is finally we should be able to make a decision, and eventually that should hit either the positive supply or the negative supply, right? So based on the decision, finally what I should get, either the decision value, this should hit the positive supply or the negative supply, right? If the delta v is greater than 0, it should go to plus VDD. If it is less than 0, it should go to minus VDD, right? So what I'm doing here is, with the charge on a capacitor, I'm making an effort. I'm making an attempt to get a circuit which can give a decision based on the voltage, right? So what do you think if I have a capacitor with delta V, and if this is delta V is greater than 0, I should make an attempt to increase this value. How can I do that? Any guess? This is not the regular amplifier approach what I have. That is why I'm just explaining in this way. I have a voltage across a capacitor, and if this voltage is greater than 0, I should try to increase this value, and that value should go to plus VDD or high. If it is less than 0, it should go to a low value. Charge it or amplify. Alright, yeah. If it is delta V is greater than 0, I should charge it. Charge it in the sense I should actually push more current into the same node, right? So how can I do that? How can I push more current into the same node to make it increase? Generally, how I can do is, if I have a block which can give some current depending on this voltage, right? So what will be this block in that case? All right, yeah. Ultimately, I'm coming to the inverter stuff. So say for example, if I have a transconductor here, now depending on this value, this can give you GM into delta V. All right, and I can actually connect this GM into delta V back to this node so that this node can eventually increase. Are you getting the point? So what I meant to say here is, if delta V is positive, push more current into the same node so that this node will eventually go back to the go to high voltage. So if this delta V is positive, what I'll do is I'll push current into the same node. And how am I doing that? That is, the current source what I have is basically a controlled current source, and I'm just using this a transconductance block there. So what I need is GM into delta V. In a similar way, if delta V is negative, what I should do is not push current into the node. What I should do, I should actually push current out of the node, right? If a delta V is negative, then also current is actually GM into delta V, if delta V is negative. All right. So are you guys with me? Are you guys understanding what I'm trying to do here? You have some voltage across a capacitor. I want to make a decision based on the voltage, whether it is high or low. Now if it is high, the voltage at the same node should keep on increasing until it reaches a supply. If it is low, if it is delta V is less than 0, it should actually eventually that node should go to the other end of the rail. Are you guys with me? All right, yeah. Now if you write the current here, the finally when it settles, if I can write the current in the capacitor as C into dV by dt, which can be equal to GM into V, where I'll assume that the initial voltage V0 is somewhere delta V. Let me do this in the next page. All right, now if I write in this way, dV by V is equal to GM by C into dt. All right, now if I integrate, If I integrate, what I'll get here is ln of v is equal to gmt by c. Or if I, therefore if I write the, one second, yeah, if I write voltage V, I can write this as e to the power of gm by c into t, where I can call this tau in this case is c by gm. Are you getting what I have done here? I have just written the current in the capacitor, and that current is actually provided by the current source. We have a control current source here. So now if I'm integrating and if I'm getting the final voltage, so for example I can write the capacitor voltage now as, the capacitor voltage can be written as v of t is equal to, I have just the initial voltage I'm considering as delta v into e to the power of t divided by c by gm, right? Or I can say it as delta v into e to the power of t by tau. Does it make sense what I have done? Going back to the okay, let me draw it here itself. I have a capacitor, and that capacitor, based on the charge, I have a control current source which is pushing current into the node, assuming that delta v is greater than 0. And based on that, I can write the final voltage across capacitor will be equal to the initial voltage into e to the power of t by tau. That is how this will charge. Are you guys with me? Can I get some response? All right. Now, if I can write the capacitor voltage in this form, what it is obvious is this is actually a first order system, right? Now, for this first order system, can you tell me what will be the pole location? What is the pole location in this case? First order system means you have single pole, you have one time constant that will give you one pole. And what is the location of the pole? What is the location of the pole here? E to the power of t by tau, right? So how will I write this? This is 1 by s minus tau. Yeah, the pole location is basically gm by c. Gm by, yeah, correct. Pole location is gm by c. Or I can write this as 1 by s minus gm, sorry, 1 by tau, right? Sorry. S minus gm by c. Right. So what do you understand from this? If your pole location is at gm by c, what do you understand about the system? What pole is this? Whether the pole is on right half plane or left half plane? Yes. Therefore, the pole is a right half plane pole. So what is the immediate conclusion if you have a right half plane pole about the system? The system is stable or unstable? Yeah, system is actually an unstable system. Or otherwise, I can consider this as a positive feedback system. It's an unstable system, correct. It's a positive feedback system. Or for the obvious reason, we call this as a regenerative feedback system. Right. Obviously, this is not a negative feedback system. And this is a positive, this feedback is there and the feedback is positive. And that is why you can see that the system is also unstable. All right. Now, bringing back this expression, v of t is equal to delta v into e to the power of t divided by c by gm. All right. So, looking at this expression, can you tell me what is the gain of this? What is the gain of this the circuit? Your initial voltage is delta V, your final voltage is delta V into this factor. So this can be considered as gain of the system, right? So why I have written gain is, now if the setup what I have, or if the circuit what I am trying to develop is based on this capacitor and a controlled current source, which can push current into the node or push current away from the node depending on the voltage delta V, and we wrote that the final voltage is equal to delta V into e to the power of T by C by Gm, right? C by Gm. Now, if I can identify this as the gain, can you tell me what is the minimum resolvable voltage? What will be the minimum resolvable voltage in this case? Again, the supply voltage VDD divided by this. If this is the gain, VDD divided by this is the factor, which is e to the power of T by C by Gm, or I can write it as Gm divided by C. Right. Now we haven't taken any circuit. I was just talking about the conceptual development of this. Now, if you look at this circuit, or look at this concept, it is very simple as compared to the first approach, or the approach A what we had, right? If you look at approach A, in this approach we need to have, first of all we need to have an op amp, a properly well designed op amp, compensated op amp, and we have to add those many op amps in cascade, and depending on the need of minimum resolvable voltage, we have to actually look for the addition or the deletion of the numbers of the stages, right? Now, but if you look at this setup, what we have is, we have a voltage across a capacitor. What we need is a controlled current source. Basically a transconductor is what we need. So with that we can actually make a decision, and the decision, since you have an inherent positive feedback or a regenerative feedback mechanism here, the voltage will be keep on regenerating either to the plus VDD or to the minus VSS supply lines. Alright. Now, in contrast to the previous case, in the previous case, if I want to increase the minimum resolvable voltage, in the sense if I want to make your minimum resolvable voltage still smaller, we should increase gain. In the similar way here also we should actually increase gain. So how can I increase gain in this case? Or how can I, to get more gain, what I should do? What are the options we have? Oh, okay, so the meanwhile, when I say that this has gain, what you can think about this is a regeneration gain over a period. All right, regeneration gain, say in a period of t, in a particular, in one period, right? In a period, a specific period, I can say. Yeah. So to get more gain, what I should do? Your gain here is e to the power of t by tau. So how can I get more gain here? Are you guys with me? Yes, either to get more gain, either I should actually work for a longer time, or I should reduce this time constant factor t, right? So when I say I should work for a longer time, in the sense I should wait for, I should actually wait for a longer time for the decision to make, and which is not practically possible, because I cannot actually wait for like days together for the circuit to make a decision, or in fact we will not generally that is even decided by other factors of the ADC or the system what we have. So generally we cannot wait for a longer time. What we can do is we can actually work on the time constant factor, right? So we can reduce the time constant factor tau. So I can do is, to get more gain, we can reduce tau. So how can I reduce tau? What is tau in this case? Tau is C divided by Gm. So if I want to reduce tau, what I should do? It is obvious from the relation that reduce C, or in fact, make C as small as possible. Make C as small as possible. So the initial voltage what we have, that is taken across a capacitor, right? So that capacitor should be as small as possible. The meaning is, or what we can do is, we should not add any explicit capacitor, rather we should use only the parasitic capacitance of the devices what we have, right? So what I can do is, no usage of explicit capacitors, rather what we can do is we can use only parasitic capacitance of the parasitic cap of devices in our case is MOSFET. All right. So again, if you look at this tau factor, let me write it here. If I look at tau I can write it as C by Gm, or in turn I can say this factor, or this is also, it is not like, we can keep on, we can as I told, C is not the explicit capacitor what we put. The capacitance is the parasitic capacitance of the device itself. That means there is some other limitation, or the limitation comes from the MOSFET itself, or this is actually limited by the FT of the MOSFET, right? Now, because you can see that tau is approximately proportional to 1 by FT, right? And FT cannot be pushed. There is actually a limit even for FT, right? So how to, just to see that, we know that Gm is mu n C ox W by L into VGS minus VT, and CGS can be written as, CGS is a product, CGS is the unit area capacitance multiplied by the area, for the various, like, it is not like always W by L C ox. It will be some two-third of W by L C ox, is very close to that. Or if I take it as W by in L into C ox, I can write Gm by CGS will be equal to mu into VGS minus VT divided by L square. All right. So if you have larger mobility, in turn that is actually giving you a faster transistor, or if you have larger overdrive voltage, in turn that will have a larger electric field which can push electrons from one end of the, like, source end to drain end. And that same way, if you can make your length smaller, the field strength will naturally increase, no? Because the length is made smaller, the strength will be more, and that also will actually help the carriers to travel faster, and even the distance to travel also will become shorter, right? Yeah. So what in turn what I meant is, if I want to, yeah, we were looking at the minimum resolvable voltage, and that can be made small by working on this tau. But again, in the tau factor also depends on the technology. That is what I want to mention here. All right. So are you guys with me? Are you understanding what I'm trying to say here? All right. So let me just take a pause or a break here, and let's have some discussion. Then we'll continue.